Well, good morning, everyone. I was just joking that my class never settles down like that when I asked them to at the beginning. So very well done. You all graduated from college, I think, and learned all those lessons. It's my pleasure to welcome you here today for the fourth Phosphorus Forum. My name is Jim Elser. I'm the director of the Sustainable Phosphorus Alliance, and along with Matt Schultz, it's our real pleasure to have you here to share a bunch of ideas about this important problem and to point our way toward really exciting solutions that many of you are coming up with. And so our job, in the Alliance is to help all of you be successful, to have impact, and to make a major advance in addressing the challenges we have to feed the world while protecting our water supply. So that's what we're sort of all about in the Alliance. And as you may know, and you can learn more about, we're happy to talk to you about what the Alliance is, but it's a members organization of innovators in the food, water sector that are dealing with phosphorus in its many forms. All right, so welcome. Here's what we're going to be doing today. If you haven't seen the agenda, we're really lucky to have an address by Bruce Rittman, who's over here. Recent winner of the Stockholm Water Prize and a real phosphorus innovator in his own right. And then we'll be talking about a project we did inside the Alliance, the Field to Watershed Modeling project, and Peter Vadis will be talking about that. During the past year, we've also completed work on a really cool new resource for the community that deals with biosolids and manure management in the North American sector. And then we're really excited to be rolling out a new initiative at this meeting, the Phosphor Sustainability Challenge. And Matt is going to be bringing us through an exercise on that to hopefully everyone understand what we're after. Then we're lucky to have some words from Kathleen Merrigan from the Sweetie Center for Sustainable Food Systems at Arizona State. She'll be talking about the cool things that are going on there. And then James Gaspard works on biochar, a really cool biochar system he's going to describe to us. Patrick Doobie will be giving us a broader view of biosolids use in the United States. And then we're going to leave some time at the end, I hope, for all of you to be able to chat and hang out and continue to network, okay? So that's, I think, it's going to be a great day. It's nice and rainy out so that no one's tempted to slip away to look at cherry blossoms. I saw them yesterday. They're really disappointing, really. I was kind of let down. No, they're actually incredible. But anyway, you can see them tomorrow. All right, so let's get started. So it's a very special year, 2019, as you're probably aware. I hope you are. It's the 350th anniversary of the discovery of phosphorus by Henning Brand. And so happy birthday, phosphorus. Phosphorus is actually older than that, right? It's billions of years old, but our knowledge of phosphorus is only 350 years old, and so maybe it's not too surprising that we still have a lot of things to learn about it and so many things to deal with. So happy birthday, phosphorus. I hope you all celebrated in your own way somewhere earlier. All right, so what did Henning Brand do? And if you go on the line, you can actually figure out what he did. So he got 5,000 liters of urine from horses and also beer-drinking German soldiers. And he brought it together, and here's the recipe if you want to try it out. You reduce it to a thick syrup. You heat it until a red oil distills up. You let the rest of it cool down. It becomes black and spongy. Get rid of the salt, and that was a mistake, as it turned out. There's a lot of phosphorus in that salt. Mix it back into the black material. Heat that up for 16 hours in your garage or something like that. White fumes come off, and then an oil, and then phosphorus, and then you pass it through cold water to solidify. And this is what these people are doing. On the right-hand side, they're boiling, doing the first stages. And if you go online, you can see some pretty amazing, crazy YouTube videos of people trying to recreate Henning Brand's experiment. It's actually very hard to do it, and in fact, Henning Brand didn't do a very good job of it. He was kind of a lousy chemist, but he was an alchemist, right? So it didn't really have good chemistry training. He left a lot of the phosphorus behind in that residue that I mentioned, and so his yields were very poor. I'm pretty sure there are many people in this room who would do a much, much better job, and in fact, who do a much, much better job in getting the phosphorus out of human waste materials. So he was a lousy chemist, but he had a very worthy goal, right, which was the ultimate goal of alchemy was to take a sort of worthless, low-value substance, base metals or whatever, and turn them into a precious substance, gold, right? That was the goal of the alchemist. And that's also our goal, and many of us, is to take waste materials that are, have negative value in many situations and turn them into a valuable material that's useful to society. So that's sort of what we're doing is alchemy. So next thing I want to do is just take you through a talk I gave at the Soil Science, or parts of a talk I gave at the Soil Science Society meeting in San Diego recently. It's a talk I gave with Phil Hagerth, who's a phosphorus scientist from England, more of a soil scientist than I am, and he and I are writing a book together. It's meant to be a popular science book, if you will. We hope it becomes very popular. But in any case, it's meant to sort of explain the phosphorus situation to a more general audience than the technical audience like this one, who's very aware of all these issues. And we sort of paint a future that that contrasts outcomes that we could reach in the coming decades if we don't do the right thing with phosphorus as we use it more intensively, or that's the phosphogeddon scenario, or whether we'll be in a more sustainable a situation where we're keeping phosphorus where it belongs and keeping our water clean and producing abundant food. And that's the phospho heaven that we hope to achieve right here together. So here's the book. We're under contract with Oxford University Press. We're hoping to publish it this year in honor of the 350th anniversary. 10 chapters. Audience is, as I mentioned, generally aiming at the reading public. And very much we've been inspired by this book that came out recently called The Wizard and the Prophet. I don't know if how many people have read this book? Okay, so great. So I'm going to get some commissions from Charles Mann, I hope now, because I read, and this is a really, really good book, actually, if you're interested in agriculture. And essentially, and this is a sort of a digest of it that appeared in the Atlantic Monthly last year. And it sort of takes the whole history of agriculture view, but bringing it up into modern times, contrasting the views of two people that Norman Borlaug and William Vaught, that I'll mention shortly. And so the book starts up, or this diagram at least starts up at irrigated agriculture up here. Domesticated animals are coming on. The moldboard plow is invented. Now sort of, intensive agriculture is being innovated. Here, down here in the diagram, we have Liebig's Law is invented. Fritz Haber and Karl Bosch are right here, and then the Nobel Prize for that, right? Recycling of organic agriculture concepts developed in the 1940s. Then there's this conflict that I'll describe between the prophets of doom and the wizards of abundance, and that's the conflict between Norman Borlaug and at the end, and William Vaught. And at the end of it, over here is this bus that's leaving for the future. And the question is, where's it going? Is it going to go off this cliff that's there, or is there a better destination that it'll reach? And so, as I mentioned, the main conflict in this book is a contrast between two types of people in science even, or in science and technology world, and man classifies them as wizards and prophets. And wizards see a world of abundance and opportunity out there in the world. They address problems with technological fixes of some kind. They believe in maximizing the biological potential of the planet and of humanity, and their catchphrase would be innovate. And they're exemplified by Norman Borlaug, who was the progenitor, it's thought, of the father of the Green Revolution and crop improvement. In contrast to them, Mann argues that in society or in science, there's been those of whom could be classified as prophets, who are exemplified by William Vaught, who emphasized the concept that there's limits to growth on the human enterprise, just like there are for other species. They focus a lot on the environmental consequences of human expansion and human activity. They argue for that we ought to be moving toward an increased harmony with natural processes. And their catchphrase would be something like cut back. We have to cut back. And it's the tension between these two worldviews that William Mann argues has motivated a lot of the scientific, environmental, political dialogue of the last half century or so. And there's consequences of that. One consequence of that may be that the battle between the prophets and the wizards is sort of unproductive in the sense that they sort of just get in each other's way. And as a result of that, the system may suffer, right? And so maybe there's a other sort of approach that's needed, and that's one thing actually that we're arguing in our book. In fact, one thing about this diagram and a lot of things that you see that talk about the environment, that talk about food, is that nitrogen gets all the press. Right? Right? Everyone knows about nitrogen, right? And nitrogen this and nitrogen that. And everyone forgets that if there's not phosphorus in that fertilizer, those crops aren't going anywhere. Right? In most situations, you really need to put nitrogen and phosphorus together in the right recipes to make crops grow optimally. And so there was no Nobel Prize for Henning Brand. Of course, there was no Nobel Prize in that period anyway. But in any case, phosphorus needs more attention, and that's one of the purpose of this book, is to raise broader awareness of phosphorus and how critical it is to our well-being. So 4 chapters at the beginning. We just want to talk about what the reason anyone should care about phosphorus, and pointing out that there's, you have about 1.3 pounds of phosphorus in your body. When I meet new people in a party, this is how exciting I am at a party, I ask them, did you know that there's 1.3 pounds of phosphorus in your body? And they go get another drink or something like that. But before I can explain to them, that it came in their food, it came from a mine in Florida or Morocco or something like that. So we don't get to that point, but I try to get to that point. But most people don't know this, right? And so it would be really great if people knew where their bones came from. Just saying, right? So that's one thing we're trying to do. When we talk about how phosphorus was produced, right, in stellar nuclear synthesis, describing that whole process, and the physics behind it. Talk about the role of phosphorus in biology, nucleic acids, ATP. We talk about the importance of phosphorus in nutrition, both for humans and for domestic animals, for bone production and other purposes. And so that's the first 4 chapters. Then Phil sort of takes over and he sketches out brings us into the agricultural period, the transition between early hunter-gatherer societies, early agriculture, and then transition to our modern situation where crops are geographically specialized in general, and we've moved animal production away from crop production in many situations. And we have also, in the Green Revolution, produced crop varieties that we call fast-growing lazy plants, that they've sort of lost their ancestral knowledge of how to extract phosphorus most efficiently from soil, because we've just been feeding it to them so easily in fertilizers. And so that's introduced in this chapter. We talk about the transition to mined phosphorus that really accelerated in the post-war period globally. This is a mine in China that Phil visited. We talk, of course, about how important phosphorus is for making the Green Revolution possible, relationships between soil phosphorus and wheat and wheat yield here. And then, and all of those things, of course, are things that Norman Borlaug or wizards have been involved in. And then the next chapter deals with what happens to phosphorus once we liberate it into the landscape. And now it's more of a wizard sort of a view of things, because we know that not just plants like phosphorus, but also algae and cyanobacteria that cause water quality problems. So we had a lot of success in the phosphorus world during the 60s and 70s when we identified phosphorus as the primary driver of water quality degradation. Here's this famous experiment in Canada at the Experimental Lakes area. So that was successful, detergent ban and other sorts of things, and advanced wastewater treatment, phosphorus removal, very successful. But now we've moved into a difficult domain, more challenging domain, where a lot of our phosphorus pollution is coming from non-point sources, and sustainability scientists characterize this as a wicked problem involving a lot of complex actors and indirect effects and delayed and subtle processes at play. A lot of problem we're having now in the current phosphorus situation is the accumulation of legacy phosphorus in the landscape. This is a product of our research coordination network on phosphorus, where we did phosphorus budgets for 3 different basins around the world, And the dark line there is the Yangtze Basin. You can see it's accumulating huge amounts of phosphorus from agricultural expansion over the last 40 years or so, whereas other basins are finally starting to move into negative balances. We're taking more phosphorus out of those basins than we're bringing in fertilizer. And so that legacy phosphorus that's built up in the landscape is going to mean there's a lot of delay, possibly between our actions and the outcomes that are produced. So it's complex. There are success stories that are out there and how we're doing better, and Phil makes an argument that we really need to look at the landscape scale, and we'll talk about that today with our some of our tools, and Peter Vadas will talk about that as well, about looking at the whole landscape of a catchment and how we need to understand that to be able to predict outcomes. And then, of course, layered on top of that, we have climate change operating. So we have new sort of hydrologic regimes that are delivering water to our landscape on different schedules and different amounts. And this is going to mobilize a lot of phosphorus, the current phosphorus, but also the legacy phosphorus that's out there. And Phil has been involved in working on this. And he estimates that with the climate change impacts, we're going to have to do even more in phosphorus management and mitigation in order under climate change scenarios than we would have had to do if the climate were not changing. And here's a manifestation of that. These are the hog farms in North Carolina that were flooded during Hurricane Florence. And on the right there is from the recent flooding in Nebraska. So a lot of places that we've put and tried to retain phosphorus in the landscape, they work fine under normal hydrologic conditions. But once when we have catastrophic flooding, such as we may have increasing amounts of in the future, many of these systems will be compromised, and that phosphorus will be mobilized into the landscape, into the oceans. And so, so that's another thing we have to deal with. All right, so and here's the really sort of the darkest view of the phosphogeddon we might be heading toward. Some Earth system scientists who model the global phosphorus and oxygen cycles are worried that we are bringing so much phosphorus out of the Earth's crust into areas where it can be mobilized to the oceans that we may produce large-scale ocean anoxia hundreds of years out before it happens and has that kind of impact. But the fact that we brought a lot of phosphorus out of its current geological pools may be threatening multi-generational effects on ocean oxygen levels. All right, so that's all bad news, right? So that sounds phosphogeddon-y, if you will. So the question is, all right, so how do we move our way out of that? This is where Chapter 7 comes in, and we start to talk about the awakening of the phosphorus sustainability movement, which brought many of you here to this room today. And so there's sort of a history of the organizations going back to 2003 of phosphorus-focused initiatives that have come on the scene, going all the way back to the Sarah 17 group that's still operating now. The Phosphorus Research Coordination Network that started my journey on this road was 2013, and the European Sustainable Phosphorus Platform, which many of you are aware of, and then the Sustainable Phosphorus Alliance are things that have most recently appeared trying to address these complex issues. And so, you know, this to me is sort of a sign of something happening. There's something happening in the institutions and in the thinkers that are out there to address this problem. And, you know, the price spike of phosphate rock in 2007, 2008 may have been a stimulatory event that made a lot of this happen. So Chapter 8, now we start talking about some of these solutions, and I've color-coded the solutions over there on the right-hand side. The Vaughtian or the wizardy ones, the ones that are sort of doom and gloom or cut back type approaches are in red, and the wizard ones are in blue. And actually, hopefully you can see that a lot of these things are a mixture, right, of approaches, right? So some of them involve innovation and new technologies, and some of them involve change in lifestyle or systems level changes that might be needed. And so the diagram there is from Dana Cardell's paper where she estimates what it'll take over the next 50 years or so to transition to a system that relies more on recycled phosphorus sources than primary mined ones over the next coming decades. And one thing you can see there, there's no silver bullet. Instead, what's needed is a silver shotgun blast of some kind, where there's a lot of smaller sort of impacts that need to be implemented. Some of them are in the food production system. That's the top 2/3, and then the bottom third are the things that will be needed to replace to provide new sources of fertilizer for the agricultural system. And yeah, and so these are all production level systems having to do with how we use phosphorus in agriculture, how we waste food, what our diets are doing, and how that contributes to demand, how we can improve crops and turn our lazy plants into industrious plants, et cetera. And those are sort of wizardly approaches. And then here are the recycling measures that are discussed in as well, including biochar, bioreactors, composting, biosolids, ecological sanitation, struvite, all these things that many of you are involved in. And now the question, is it going to be enough? Are we going to get the phosphoheadin or not? What's it going to have and what's it going to take? There was a paper that came out in Nature, I think, yeah, last year, where they estimated phosphorus use with respect to the planetary boundaries framework that's been developed and the safe operating space concept, and that's indicated in the green there. The red bar is the projected increase in phosphorus application going forward. I think that 2030 or something like that is the time scale here, and you can see that the red bar is way over the planetary boundary, which that black dot is the mean of the current versions of planetary boundary for phosphorus use. And then the other bars are different mitigation measures that can bring us down from that red bar. The first ones have to do with different waste. Those are food waste and recycling approaches are in yellow there. Technological innovation in farming and other sorts of sectors is shown in gray. Green are the changes you can get from dietary shifts with less meat in the diet, for example. And then the blue ones are the combination of some of all of the above, either in a high adoption scenario or a medium adoption scenario. And you can see it's really only the combination of strategies that bring us below the planetary boundary for phosphorus. And so it's going to take a lot of things to go right for us to get there, right? So we got to get all that stuff on board and operating at a reasonable scale to avoid that outcome. And so that's a little depressing, maybe, but it's a rainy day. Maybe it's appropriate that we're a little sad, I don't know. But I don't like to leave on a depressing scale. And so here's another way that I like to think about things, and that many of the innovations that are rolling out and that many of you are involved in, I'm hoping are going to spread very rapidly. And I take some solace from renewable energy estimates that have been put out there. So this is a graph I found online as someone analyzed the annual rate of photovoltaic additions to the energy system globally. And that's the black. Black is the actual addition. It's a rate, gigawatts per year, so it's a rate. Okay, so that's the rate in that given year. And what the colored lines are projections made by the International Energy Agency in a given year. And so you can see that in a given year, what the IEA does is it just assumes that the rate of adoption of photovoltaic will be the same as it is now, right? So, and they just always get it wrong. They're way underestimating the rate at which photovoltaics are coming online because they think that now is just going to be constant. But instead, what's going on in photovoltaic adoption is an exponential function. It's an exponential process, so the rate is increasing. So it's an exponential change, and so it's exponential changes that produce rapid transformation of systems, and so that may be what's playing out in the energy field right now. And my optimism, the reason I get up in the morning and organize events like this, is I think that we can also get onto such a trajectory for how we use phosphorus in agriculture, for how we use it in animal production, for how we obtain phosphorus from different sources, and get those changes rolling out in an exponential way that can solve the challenge on the left going forward. All right, so how do we get to do that? Today I sort of made a dichotomy between prophets and wizards, and you can identify yourself. Maybe I should get a little survey and say, where do you see yourself on that gradient? Are you someone who's really obsessed with the water pollution side of phosphorus, worried about all those impacts, and and think that we need to do a lot less of everything? Or are you a wizard who has new technologies and innovations that you're ready to implement to address things? And I think most people are sort of probably in here, because many of the innovations that you're seeking are to address problems that the prophets have identified, right? So it's sort of a mixture. And so really, I think what's needed, in addition to having those who study the problems that are emerging, those who develop the engineering technological solutions that are needed, is a different type of person than a wizard or a prophet. And we call them systems innovators. They're sort of systems level thinkers who have the whole picture in their minds and are able to develop the frameworks by which innovation can emerge to solve problems. And so those are the types of scientists we think and engineers and systems thinkers that need to emerge in the coming decades for us to be able to get around this problem. So with that, that's why we're here today. We're here today to try to bring wizards and prophets together. We're here also to bring systems innovators together with those to address the phosphorus issue and to bring us into a future that we can be proud to have left to our grandchildren, in which we have addressed the food and water needs into the future. So thank you for listening. Oh, I'm right on time. That's good. And maybe I'll take a question or two. Yeah.
Yeah, and actually, if we could get people to talk into this mic, and if we could get me to actually be able to walk through the room, that'd be better, because we're recording this for YouTube. It's going to be rebroadcast later.
Thanks, Jim. Nice talk. And I have the question the last slide raised, which is, so you raised the PV thing, and in my lay terms, I understand that there's a market incentive and a financial incentive for that exponential curve to happen. And I'm wondering what you see as a business model that will help mimic that exponential curve in the complex phosphorus world.
Yeah, that's right. So so the reason photovoltaics are taking off like this is, of course, because they're starting to become cheaper than other sources of energy, right? And that's true for several reasons, because photovoltaics have been stimulated along a bit by federal level investments and other sorts of R&D investment already to make photovoltaics more effective. So that hopefully will continue to go forward for folks working on this problem on the recovered phosphorus side of things. We need more investment in new ways of doing that. And I think there are people here who are implementing some of those, and some people here are still on the research side of things we haven't even thought of yet. And so we need more of that. One thing that challenge we all have, right, is that recycled phosphorus products are, on one level, still kind of expensive compared to other sources of fertilizer. On the other hand, if we had a way of calculating in the avoided costs of, so for example, if we recycle manures into usable fertilizers, then we avoid all the negative outcomes of excess manure on the landscape. Right? And if those costs were somehow accounted for, then the recycled phosphorus forms might be cheaper. But there isn't a way right now by which those price differentials can be incorporated. So it's not, I don't have a good answer to that question, Ned.
Right. Maybe we should move on to Bruce.
Yeah, that's great.
Thanks, Jim.